example. But we're continuing on with the discussion of X-ray spectroscopy to keep the flow of X-ray spectroscopy discussions going before we jump over to neutron scattering and then Raman spectroscopy, both of which can give us information about local structure, but also some average structure in different length scales. Speaking of length scales, this you've seen a million times, but I just want to remind you where we are in terms of the length scales that we're trying to access. So we're continuing to discuss the probing of the chemistry via spectroscopy of cycled battery materials, but also some of the decomposition products. And today we'll actually touch a little bit upon liquid electrolyte, which we have not discussed at all, because we've been focused on emerging solid electrolytes for all solid configurations for next generation batteries. So we'll talk about XPS as it relates to XAS because there's a lot of similarities given that they're both spectroscopic techniques. There are differences, obviously. That's what we'll talk about and why one would utilize one technique over the other, or rather sequentially order them in terms of accessibility and what kind of information you want to get out of it in terms of materials diagnostics. I've also just recovered from a cold, so I'm now not symptomatic enough to cause you great concern and alarm. So in terms of databases, the handbook on X-ray photoelectron spectroscopy has had a few iterations now. This is a great resource if you want to dive deeper into the theory that we'll touch upon at the beginning. And I've also highlighted the CASA XPS manual because while it is a manual, it has details on the operations of the instrument and data analysis, of various instruments, I should say. It is really a wealth of information when it comes to trying to understand and also interpret XPS spectra. And this goes back to what Modesta was saying about X-ray absorption spectra, which is one could overinterpret if one doesn't have enough chemical information, or one overinterprets because one has, perhaps other, or either you have more information you're trying to squeeze in and try to overfit the data. That can also happen. So, so the data should be handled with care, but the manual really goes into great detail about all the conditions and the types of background fittings, spectra deconvolution that you can do, what they really mean, like what is a pseudo void and all of that, and how to interpret all these X-ray interactions with matter. So down the rabbit hole one can go if one needs to go down there. And the NIST database is also a great resource. If you ever want to compare your binding energy of a particular chemical with a lot of other known XPS spectra for other elements with the same oxidation state and similar coordination environment as your species, this is the database to go to. Because if you think, oh, should I calibrate? Is it, half an EV, sorry, 0.5 EV off or so? This is a really good database for that. And the last three resources are really good primers, particularly for different elements. So if you're exploring, if you're working with a new compound or new to you, and you're not familiar with a particular binding energy or the spectra that's typical of these elements, this is a really great starting point so that you don't have to go into the weeds if you don't need to. It's a really good introduction for different elements. So XPS simplified and XPS fitting are two really good starting points for that. So you have, surfacey and also more detailed information for later on. Okay. So in terms of what information you can get out from XPS, it's pretty similar to the lists that we discussed for X-ray absorption spectroscopy, right? You can, it's a surface sensitive technique. So if you're trying to probe an interface that you've just exposed so that you can study the surface, it's a good technique for that. It's also appropriate for understanding coordination as well as oxidation state with chemical specificity, because different elements and different oxidation states have different binding energies. Spatial resolution as well, because you can map depending on where you point your the X-ray source. Now, I should say there's a caveat, which is you're also limited by the depth that you can access. So, depending on what kind of information you want both in surface, this technique will have its limitations. And another strength is that this can be a quantitative technique. It doesn't have to be just fingerprinting or identification of oxidation states and species. You can quantify the relative, well, I wouldn't say phase fractions, but the different chemical moieties that you have on your surface. You can, really track that and do a quantitative analysis with calibration and standards. Okay, so we'll go over the theory and some practical case studies. In terms of theory, I'm going to go over, as we've been doing, theory and also some operational considerations and limitations as we discuss the theory, right? So this diagram is pretty similar to what you've seen with X-ray absorption. It can probe the different energy levels by having an incoming X-ray source. And in terms of a laboratory technique, these are often limited by two common lab X-ray sources, aluminum and magnesium, K alpha. And that allows you, that amount of energy, 1,000 to 2,000 EV, allows you to excite a lot of core electrons and also electron energies that are above the core electrons. So you can already tell that, if you're operating at about incoming 2,000 EV, right, you're not really able to access higher energies than that. So that's where you can transition to, let's say, synchrotron, if you really want to probe the higher energies, like the 3D transition metals start off with 5,000 EV for like scandium K edge, right, 4,500. So you need higher energies than that. And so similarly to X-ray absorption, the photon will then interact with the electronic structure, and then you generate the photoelectron. And this photoelectron will now, interact and be detected by a detector. And now technology, when it comes to X-ray photoelectron spectroscopy, has come a long way in terms of resolution, and that has everything to do with both the vacuum chamber, the ultra high vacuum chamber, I should say, and also the detectors that are available, and also what's called pass energy. So we'll talk about that in a little bit, how you can get higher resolution by controlling your pass energy. But the importance is that you need a monochromator so that the X-ray beam, when it comes in, is as fine resolution as possible. And then the emitted photoelectron will then be guided through this electron energy analyzer, which will then be detected. So it will spread out the energies. And what's also really interesting is that this technique allows you to study the different depths within a material. So here, if you have this heterostructure, film A all the way to film C, you can actually carve away certain levels of these films, so C and then B, and they exposing different layers and then getting quantitative information from this technique. The other way you can also do it is you can probe different depths by using different X-ray energies as well. So you can switch from, if you have the capability, you could switch from a aluminum source, a magnesium source, to a silver source, and you can probe without like etching away the surface, because you're able to access different layers that way. So it's a really powerful technique, but we'll also talk about some limitations when we talk about some of the operations a little later on. Now, in terms of, what kind of information can you get, and typically what will people plot, is is probably the more useful way to think about it. In terms of the information that you get from XPS, all it has to do with the material itself. So the X-ray source that comes in, so that's this E sub photon here, right? It has some wavelength and thus some energy, some wavelength lambda, and that depends on your X-ray source, your metal source. Now, to eject, let's say an electron from the 1s orbital, you need to overcome the binding energy of that electron from the orbital. So you kick it off. Typically, if you're at 1000 eV for the various elements you have, there's going to be some leftover kinetic energy, right? This ejected electron now has some excess energy, and thus they can go into the vacuum. It overcomes this, this work function that's defined as the energy between the Fermi level of the material and the vacuum level. And so all these three components together, the kinetic energy, the binding energy, and the work function, has to total the incident X-ray energy. Okay. So with these three components, you can form three different equations. You can basically rearrange the equation so that you get the information that you want. So if you know the total energy of the incident X-ray beam, and you know the components are the binding energy of that particular 1s electron for the different species, different elements, you can measure the kinetic energy from your detector. Your detector can measure that. And you know what the work function is. So you can then rearrange it and say, okay, I'll plot the kinetic energy that I measured, or I can plot the binding energy by just rearranging, because I know my incident, I know the kinetic, and I measured it, I know the work function because I know what that level is, because that's how I calibrate my detector, the electron energy analyzer. So typically people will plot either the kinetic energy or binding energy. I will say overwhelmingly people will plot the binding energy, and that's what we'll discuss, and that's what the plots that you'll see, they're overwhelmingly the binding energy, because what you want to get at is what was the binding energy of the species of the material that that the electron came from. Okay. So you can see that your analyzer can sweep across different energy levels, as you can see here. So here's a nickel foil, a nickel standard. So there are many papers like this. If you ever need to know, did I calibrate correctly, you can just look up the standard XPS spectra, and this is just an example of a nickel one. So if you have nickel, you might want to look up some of these standards. And so what you see is the higher binding energies are the core states. So there's 2s, the 2p, the L3M. So this is OJ. So that means you've excited an electron, goes up, and then one electron will then, from the M level, will actually be kicked out, and then another electron will then go into the vacuum. So it's a more complex process, but essentially it gets ejected from this L3 to begin with. Okay, and then there are some other species that you see here. Oxygen, nitrogen, which is pretty typical, because even if you're at ultra high vacuum, which is 10 to the minus 10 torr, you can still have, that's not zero, right? I mean, that's 10 to the minus 10 torr. And so you have always some oxide and probably some oxidating nitride, particularly for the 3D transition metals. And then adventitious carbon, so that means there's always residue everywhere, right? You can just breathe on it and be adventitious carbon. And then nickel 3s, so on and so forth. And the detection, you can see by the intensity also that it gets smaller and smaller, and the binding energy gets smaller. And there is a sensitivity limitation at, especially if you're 50 and below, do that with care, which around 50 is also where lithium is. So lithium, one has to really measure that with care, especially if you're working on lithium-ion batteries. But that's the case for SEM and any other SEM, EPS, and any other characterization techniques that we've talked about. Okay, so the survey spectrum tells you, if you didn't know, maybe you had some chemical intuition, but if you didn't know, you would sweep, the entire, a large range of binding energies to identify all the species that are in your system that you should be looking at, and they should be there, as in the species that you expect should be there, and the species that you don't expect should not be there, as in contaminations, impurities, right? So if you pick it up, that's indicating that your sample prep is, could be questioned. Now, here's an example of what happens when you have overlapping spectra. So here is a molybdenum sulfide sample. So if you were to take one of the dominant peaks, like molybdenum 3D, if you had a sulfide sample, you could look at the sulfur 2s, but you can see that there's overlapping between the sulfur 2s and the molybdenum 3D binding energy. So while this fitting is fine, as in publishable, there are some considerations that you should keep in mind, right? I mean, you can always deconvolute and reason and cross-correlate with other characterization techniques to try to understand the amount of sulfur to molybdenum species. And for this particular study, we were really interested. That was the core of the study, is how much sulfur was there upon discharge and charge, upon lithiation and delithiation, and how does the structure change to accommodate the extra lithium ions. So while this is sufficient in terms of the deconvolution of the peaks to try to quantify the amount of sulfur to molybdenum species, the fact that these two overlap also makes it less than ideal. So there you would try to find another sulfur edge, say, or another binding energy. I said edge. Another binding energy. Okay. So in terms of operations, one has to take into consideration that this technique is a surface sensitive technique. So the depth that you're able to probe in a sample is limited by the X-ray energy, the electron energy. And that has to do with something that's called the inelastic mean free path. And so this has been empirically worked out. And so this is a fabulous 1996 study that has been cited quite often, but this is the number that people often quote, and it has origins from the mid-90s of why it is that XPS is a surface sensitive technique. Now, who has done XPS methods? Okay, not the majority. Now, what depths have you been able to access with sampling of your material? $45 micron. Oh. Oh. Mm-hmm. Okay, a few. So you would say less than 5? Less than 10? Okay. Do you find that there's variability?
Yes, depending on the so you have.
Mm-hmm. Yeah. Mm-hmm. Right. So that's one subset of challenges, I would say, and really material and sample dependent experimental setup. And that is really the takeaway message in terms of the operations, which is even though you can calculate what is the inelastic mean free path, that's this this G1 equation that it's often called, you can fit these K1, K2 parameters, and they're very small numbers. They're like 0.00 XY. And you can look up these K2, K3, depending on the material you have, the atomic volume, and also what's called the number of interaction prone electrons per atom. So you can look these things up and fit it for your specific material. And what you get out, and so you can see here these numbers are quite small. So what you get out is, depending on your electron energy and your atomic number, also that the elastin free path or electron energy up to about 2000 eV is really about 10 nanometers from the low. That means that's the path of which the electron will not run into something else and then get scattered and then lose energy and then gets buried. So that goes back to this right here. So ideally what you want is for the electron to actually be able to escape out of the surface of your sample and be detected, right? And that's not always possible because sometimes they just get trapped. So, excuse me. Excuse me. So depending on the energies that you have access to, which at OSU were really, I said I was asymptomatic, but if I speak too long, this happens. Excuse me. Then we're limited to the more common one, which is magnesium and silver. Even the new XPS instrument that's coming online to replace our current one, which is already on its last leg, it's still the same source. It's the same aluminum source. Okay. Now, so sample prep is key. Variation in depth will cause you to have different types of signal. The intensities may change. And so in terms of the sample type that you'll have, I think a lot of us will have powder samples that are basically not perfect. Unless you have a beautiful layer that is flat and the thickness is uniform, you're going to have some signal attenuation. You can also have some charging effects, which we've seen, things like SEM that can cloud the signal and also distort the resolution. So here you see a signal from the chlorine 2p peak. So the 2p 1/2 and the 2p 3/2 here. Higher binding energy is the 2p 1/2. And so you see without charging, you see these spurious peaks that are not real, as in they're not physical. They're not attributed to a physical phenomenon, which is the orbital splitting. And so this can really present a problem if you're dealing with semiconductor materials, which is often the case for a lot of the battery materials. And so what can be done there to mitigate these issues is you basically charge and neutralize. You have a charge neutralizer that if there are charges that are coming off, you can then just basically evacuate those charges. And so you charge neutralize. And that is pretty effective operationally. But if you ever get any signal that looks non-repeatable and also curious, as in you have chlorine, you should expect a 2p 2p 1/2, 2p 3/2 peak like this, then that means, right, then it should be resolved. You should be able to resolve it. So that's another indication that perhaps something is off operationally. Okay. In terms of setting the pass energy operationally, when you're doing a survey spectrum, you're just scanning through all the energies that you can possibly scan through. Or if you know the material that you're dealing with and all the elements that are in there, then obviously you would only scan the energy range that is relevant for the elements that are in the material. But setting the pass energy, so you can see here that going from 40 eV all the way down to 4 eV, you get higher resolution, as in the full width half maxima are more resolved. But this takes time. This takes a lot of time. This can be a 1-hour scan, and this, depending on how this looks, this could be average over 3 scans, and that's what you should do. So, but if you're just trying to get information about species identification, then you could do like a 15-minute scan at lower resolution and just pass through before you spend more time in getting high res data. You can also go as low as, or sorry, as high as 80 EV to get, like, let's say, a survey spectrum. And so for the silver 3D, you could see here that you can get this higher resolution with, a detector that has, better analyzers, and you can get the full width maxima to be, more well resolved, and you can run some really nice scans that you see here. But this, it's one of those things you have to make a decision. Can you live with 10 EV, 4 EV, or 5 EV resolution? You really have to run 2 EV, pass energy to get the information that you want to resolve. If you're trying to, let's say, do relative quantification, this is what you really need. Do you need, or is it overkill? Right. So with all these techniques, you can always get higher resolution, but do you need it? If there are no overlapping peaks, can you live with something like 10 EV, pass energy, collect 3 scans at 20 minutes each, and then be done with your data collection? But you can always get higher energy. Okay. And now some of you work with nanomaterials, some of you work with 3D transition metals. So air sensitivity is a huge issue. And this technique is highly sensitive to that. So if you load a sample without, for a material that is air sensitive, you could see here that with the glove bag that's been mounted, that the iron spectrum is maintained. But if you, let's say, if your sample is air sensitive, but you expose it for even under 5 minutes to get it out of the device that or the battery, and then load it into the XPS instrument, you can see here that you're going to get shifts and spurious spectra peaks that are non-physical, right? I mean, as in they're not represented. Well, they are physical. They indicate that you have oxidized your sample, but they're not very useful for trying to understand the species that have evolved as a function of, like, say, cycling. And so that's something to take into consideration when you're sample prepping. Now, in terms of the binding energies, what you'll notice is that with all these plots, especially if you're looking at the orbital angular momentum of 1, so that's your P, right? Your 2P, your 3P. You always see these doublets. You see here. Now, Patricia had a question about principal quantum number and the rise of these of the separation of the peaks. Now, anyone wants to venture a guess as to why there are always these doublets for orbital angular momentum that are greater than 0, aka not an S orbital? Okay, so it has to do with spin orbit coupling.
So,
So there's spin orbit coupling, which is a spin angular momentum coupled with orbital angular momentum. Does anybody want to review after that? Okay. We're all squared away with quantum spin number, or principal quantum numbers and spin. So that's great. So the separation then, at least for sulfur, will be specifically 1.16 eV, but this separation is different for different elements, and the area is based on the degeneracy. Anyone want to take a gander as to why this ratio is 1/2?
When you go, for example, to the level, you organize.
Okay. What's another way of generalizing that? So if you didn't have P, let's say you're looking at T or F orbitals, what would then be the expected ratios for these P's? That's in the arithmetic. This doesn't have to be a modest activity. This could be a complexity. I'm confident in you. Okay. Okay, all right. Happy to review. Is there consensus? All right, there's general nodding. All right, so let's review, because the origins of the separation and also the ratio all has to do with the electron configuration, right? So we've covered orbital angular momentum, spin angular momentum, which added together or subtracted will give you the total angular momentum. So if they're parallel or anti-parallel, so L plus S or L minus S, okay. Okay, so let's review. If you have a p orbital, L is equal to 1, so S is equal to 0. That's your angular, that's your orbital angular momentum. So if you have 2p, then you can have the L plus S, so their total angular momentum could be L plus S, which will give you 3/2, so 2p 3/2. Or you could have J anti-parallel, so L minus S, which is now one spin, sorry, S is 1/2, because electrons are fermions, so they have S spin of 1/2. So you can have 1, so L is 1, plus 1/2 is 3/2, 1.5. Or you can have anti-parallel, which is now 1 minus 1/2, which is 1/2. Right, so now your total angular momentum is 3/2 or 1/2. So 2p 1/2, 2p 3/2. So you have that. Now, in terms of the degeneracy, you have to take into account the magnetic angular momentum, mj. And this can be mj plus, has to be plus or minus 1. So you have plus 1/2 minus 1/2, plus 3/2 minus 3/2. And so for J of mj, so if you have a J of 3/2, there are 4 states. So 1, 2, 3, 4. For 1/2, you have plus or minus 1/2. So you have only 2 degenerate states. And thus the ratio is 4:2 or 2:1. Or flipped what I said before, which is 1/2 to 3/2 is 1/2. Or 3/2 to 2/2, 1/2 is 2. So if you do the same arithmetic calculation for the total angular momentum for d orbital versus, let's say, an f orbital, so L equals 3, you can calculate the degeneracies to be
6 to 4, or 8 to 6.
So that's the rise of the ratios of the areas, and also why you have the doublets, is because you have total angular momentum change. Okay. Is that clear? Okay, so I just, flipped it. So you can do 2, or in this case, it's 1. All right, so now let's go on to some case studies and see how we can actually apply XPS to quantify or fingerprint and identify the species that we have to try to understand species and structural evolution upon lithiation and delithiation, or sodiation and desodiation. So what's great about XPS is, unlike X-ray diffraction, where we have diminished signal because of the existence of amorphous material, here you can identify the chemical species even if you have an amorphous material. And so one of the compounds that we've looked at previously are these molybdenum polysulfide materials that have been investigated because we were interested in minimizing the polysulfide shuttle effect by anchoring the polysulfides that form with the lithium. And so it's a chemical linker. And so here, just to review, you've seen this already, but the cathode is just the active material. So it's labeled as SX because, and this is something I didn't go through before, because the sulfide chains are variable. They have an average length of 4, but it could be between 2 and 6, and so it's labeled as X for that reason, but it's about an average of 4. And so just a half cell, the anode is lithium. It's a pretty standard LiPF6 and ECDMC, standard 2032 coin cell. And here the source is a monochromatic aluminum K alpha source. Pass energy is both 20 and 80. So high res, low res. You do the low res first, survey spectrum, and then high res. Okay, so here is the schematic of what we think is happening upon lithiation. These sulfide chains are being broken so that the lithium ions can come in. And then upon delithiation, the lithium ions migrate back and these sulfide chains are formed again. And the role of the molybdenum is to anchor the polysulfide so that they don't go over to the anode as much. Right? So what we're trying to understand from XPS is, how are these chains moving around, and what is the quantitative relative values of these chains that are breaking and forming. And so what we can see is that we can track the different sulfur species. So before we looked at different oxidation states of sulfur, right? We had sulfur, sulfite, sulfate, so different oxidation states. So we can apply that similarly for these polysulfides, because if you have the polysulfide species, you're expecting a 1- oxidation state. But the binding energy could still change depending on whether or not the sulfur species are the bridging sulfur or the terminal sulfur, which would be at the end. Right? Because these sulfur that are in the middle of the chain, so these bridging sulfurs, they are covalently bonded, and thus they would have higher binding energy. So that's how we're going to be able to distinguish between the higher binding energy bridging sulfur or sulfide and the terminal species. So one would expect that as you lithiate, if you're breaking these bonds, you're forming more sulfide species at the terminal. So you would expect the blue to increase, and that's what you see. So you compare it, and then the area, as you lithiate, so this is 2 volts, you discharge, so the voltage will become lower. You see that the blue is increasing, and then it decreases, and then it decreases a little more. Now, this data is presented because this is a real sample. So if you look at this species at 1 volt, which is where the lithiation stop, you can see that the signal is quite noisy. And it is what it is, as in there's a lot of SEI that forms, and if you have a thick layer of SEI that forms, the solid electrolyte interface will interfere with your signal. So even when you have high resolution before, the SEI will diminish your signal. And so, you know, it is what it is. You know, that is the signal. Now, one can argon etch and try to get a better surface. Sometimes when you do that, though, you're going to interact with your sample, and you're going to cause reduction in other species, you know, that will form as a result of the processing. And so for this publication, you know, we left it as is and just reported this is the data, but the trends hold. Now, interestingly, what's happening with the molybdenum side is that nothing is changing. It's quirky to publish and say nothing is changing, or nothing significant is changing. And that is in line with our hypothesis that upon lithiation and delithiation, what's happening is that your molybdenum linkers are intact. It's the polysulfides, these sulfide chains that are doing the charge storage. They're being broken and reformed. So one would expect that the linkers would remain inactive and thus not significantly change. So the null result is still valuable and significant to report, even though at 1 volt, the signal is pretty low, and one could do fitting, but there's so much overlap that it's pretty insignificant to say something significant. But the data is reported for, you know, full transparency of what's happening with the battery material. Okay. So another case study that's pretty powerful for the use of XPS is to understand interfacial phase evolution upon lithiation, or in this case, the deposition of lithium onto a solid electrolyte. We talked about lithium lanthanum titanate before as a solid electrolyte that is in the middle in terms of ionic conductivity. It's actually not stable against lithium metal, but it is a really good model system to try to understand what's happening upon lithiation, delithiation, because you can probe the reduction states and the oxidative states of titanium during the cycling. So what's also really interesting about this study is that they're trying to ask the question, what exactly happens? Because if the hypothesis is that lithium lanthanum titanate is unstable against lithium metal, then one would expect both a chemical decomposition, because it's on a stable interface, or if it does form a stable interface, then you would expect, you know, lithium ions to be transported, and then the electrons to be transported, you know, in the external circuit and all this, you know, thing, you know, wonderful. But that's not really the case, right? I mean, one is going to expect the reactivity, and also what is the mechanism of the reactivity? As in, you know, is it just going to be a decomposition, and then your solid electrolyte interface will form, and the SEI may or may not be useful for you, as in it might be ionically conductive, it might be not, it might be electronically conductive, it might be not, it could be mixed. Surprise, it is. It's mixed. The punchline is that it is. Or it can form some metastable SEI. And so we can detect that with this study. So, so here, this is the study. And in fact, the study looked at in situ deposition of lithium. So instead of having your solid electrolyte pellet and then depositing lithium and then taking it to the instrument, which can already cause decomposition and phase evolution at the interface, which has actually been shown by a later study, a 2016 study by the same group, that the time that it takes for you to walk from your glove box over to XPS is the amount of time that your material has already been placed. Right. So what they did here is, here you have the sputter gun that will hit this target, the metal being lithium, but it can be anything. And they've done control studies of gold. You can deposit gold for symmetric cells that's ionically blocking, but you can deposit lithium, onto your sample. And then you can do XPS, so all within the same chamber. So the sputtering gun is now in the chamber under high vacuum, ultra high vacuum for XPS. And then you can detect and try to figure out what interface you have and what interfaces are developing. So this is extremely useful for people developing interfaces and trying to form formulations for, let's say, artificial SEI, because if you know what's going to form and if it's useful, as in it's ionically conducting, then you might want to have just form the artificial SEI because it's thermodynamically going to get there. Okay. Yes. Interface is a material and then another material. That is the interface. Right? Just two things on things. That is the interface. Interphase is this region where phases can form, and they only form at the interface. As in, if you just had your sample, this yellow region, and let's say you put it in air or whatever surface, that those phases might not form because it's not interacting at the interface with a dissimilar material. That's causing it to decompose thermodynamically or what have you, or chemically, electrochemically. So these interphases, and it's defined by what the interface is. So the solid electrolyte interface is are the phases that only form at the solid electrolyte interface. So, right. So what exactly is happening? Upon lithiation, so I should say, when I say lithiation, deposition of lithium, not actual lithiation electrochemically. So this is just deposition of lithium. What you see is as a function of deposition time. So now that means you have more and more lithium coming in. So lithium metal coming onto this LLTO surface. What you're seeing is the emergence of here, you're seeing this peak. So the +4 state of titanium, and then titanium gets more and more reduced to the +3 state, the +2 state, and then the 0 valence state. So you're forming titanium metal. It's reacting so much that you're forming now titanium metal, which is not what you want, right? Because solid electrolytes should have high ionic conductivity. And if you have a metallic species in there, one, now you have an inhomogeneous material, but two, you have pockets where it's electronically conductive, which is extremely detrimental. Okay. So that is a first pass. That's what we can see. Quantitatively, you can fit all the peaks and try to say something about the evolution of the titanium species. So here, already within 300 minutes of deposition, you don't have to wait very long. You already see the reduction of titanium to 0 valence titanium.
It's like the deposit different later.
Yeah. That it does. So it's more lithium to react with the LLTO, particularly the titanium that's being reduced. But also, you're losing lithium at the interface, and lithium is now intercalating into LLTO. So you're inducing intercalation mechanism and a chemical reaction. So many things are going on. And how you know that is you look at the deposition time. So the more you deposit, you can see the areas of titanium metal just increasing. So basically, this reaction is just increasing with the amount of lithium ions that are increasing. Okay, so this is already telling you that just a little bit of lithium will react with LLTO. Okay, so and concomitantly, you see, the +4 state decreasing and all the other oxidized state, reduced states increasing. Now, the role of oxygen and lanthanum, interestingly, what you see is lanthanum 3+ is actually stable against reduction. So you don't see formation really of the +2 state or even lanthanum metal. So what's really happening is the titanium is being etched out of the LLTO. Okay, so you could think about materials design. Okay, how do I stabilize titanium being reduced? Either I have another species that's a little bit more reductive to try to stabilize LLTO, or I accept that, you know, this is what's going to happen, and how much is it going to happen? As in, how much titanium am I going to, is going to come out, and can I live with it? As in the electronic conductivity, is that the, how detrimental is that to like the electrochemistry? So there you can begin your materials design based on what you know from the XPS. Good. Okay, so then you can track all of that as a function of time, the number of titanium species oxidation states as a function of how much, so how much lithium per formula unit. And so as as the amount of time is increasing, lithium is increasing, and what you've seen before, but now just graphed in this overlay that a titanium 4 is decreasing. Now, in terms of how do you know how much lithium you have to do a calibration study, because this is plotted as a function of time. And so you really have to do a separate calibration to see how much lithium is deposited as a function of time, you know, when you don't have the LLTO, because what's happening is when you do it on just LLTO, you have a reaction with the interface with LLTO. So you could just deposit lithium on like some other metal, some other target that's not reactive, but one would have to do a control study to know exactly the thickness and the amount of lithium that's deposited. But this is a great study to show that you can do these kind of probes all in one go, even though it is extremely challenging to operate in ultra-high vacuum. You can still, you know, do these nicely controlled studies to look at the type of decomposition products that you have. Okay. The next example is sodium-ion battery electrolyte and additives, but we will continue that next time. Questions? Additional questions?
Smaller than the same.
Yeah.
On slide 7.
Okay.
So I know that, so we know that and then we're measuring the kinetic energy of electrons.
Yes, the kinetic, yes.
So then then the subtraction gives us the sum of the binding energy and the work function. And so I'm wondering then what's the step that where you're isolating the binding. You mentioned something and the work function.
Yes, because you know the work function from the Fermi level to the vacuum, that's based on the detector. So you know the work function of the detector. This is new.
But isn't it also material specific?
Yes, and this is all mapped out.
Okay.
Yeah, all of these values are mapped out. So there are databases, you know, usually if you go into Xray, XPS room, there's a folder that is like this thick. And it's literally every single element. Okay. That's been worked out already.
So is that just like you're telling like the detector, I suspect there's no.
Yeah, when you,
that work function?
yes, so when you set up the experiment, so this is operational / theory. Okay. Is that, excuse me. Right, so when you scan and when you pick your energy, it's now built into these instruments and the software that goes with the instrument, that when you pick a certain energy, that you're really looking at a particular element, or at least several elements, because sometimes they're overlapping, like the K, or sorry, the 1s binding overlap with, you know, some Auger with another element, and sometimes if you let the computer guess, it will say, oh, you have osmium or technique, you know, like something ridiculous that you know is not sensible. So, but it's all tabulated in the software, because this information is already known. Right here. Now, that's, okay, well, that leads me to a side comment that you didn't ask about, but it is important, which is because these peaks are overlapping, it can arise that if you happen to have coincidental peaks or peaks that coincidentally overlap, and if for whatever reason you cannot isolate, I don't know, if you have a really complex system and there are a lot of peaks that overlap, like you couldn't get away from molybdenum 3D and 2S by picking an S2 peak. Let's say that if you couldn't do that and they overlap, or there's an OJ peak of another element that's also in your system and you just can't. I'm trying to imagine offhandedly like what this case might be, but I can't think of one because usually you can isolate well. Then yeah, the peak fitting just has to be done with like a lot of care and would sample a lot of, say, you know, a lot of points in your sample to make sure that, you know, you're not overfitting. The other thing is operationally, the full width half maximum, you know, you can't just willy-nilly say like, just fit a Gaussian or fit this like pseudo void and whatever I get is whatever I get, right? I mean, there has to be some constraint, and what those constraints are you can base that empirically off of like similar spectra or similar samples. So if you know you're working on liquid electrolyte, you're looking at decomposition products of the carbonates and all of that, you look up other carbonates because people have done carbonate calibration and say, okay, you know, if I only had carbonate, what would the full width half maximum look like? And thus I can constrain it and not just have like this broad peak that I can say, well, yeah, I have some, you know, so there's a lot of sensibility and reasonableness that goes into it, but it's, but that's not to say that that overfitted spectra haven't been published before, you know, so I say that with, you should do it with a lot of caution. Okay, that's my diatribe on don't overfit your spectra. Oh, yeah, okay. Yes, yeah, you see this noise? Yes. The answer is yes. In terms of difficulty, these signals were collected by put the powder sample down, and then there's a tamper where you can like pat down the powder and get it as flat as possible. And even then, right, the limitation is that you're human and you can't press it down as any more than you can to try to get it flat. So this is the best attempt at getting it flat using, you know, standardized preparation technique. It's, yeah, it's challenging. It's probably an understatement. So this data is also averaged over 3 scans and also averaged over like multiple sites, not just like one site. So each one of the scans is about 45 minutes, so times 3, so that's an hour and a half. And then you do multiple sites on multiple electrode samples to make sure you gather enough statistics. You're looking at almost a day, if not a little over a day, just to make sure that you're not, you know, getting some spurious data because you looked at only one site. All right, so if there are no more discussions, we'll adjourn and then pick up next time on this before we move on to neutron. All right, thanks everyone.